Everybody, in a prior video, we looked at developing a mixing model and we used these data from the Chaos Crags. Here we're going to look just at Dome A and, Dome A through Dome F, but just the felsic compositions that have relatively high silica content. What I've done here is I've set up a mixing model for MgO and SiO2, and I've used as in the prior video, we've used this equation for mass balance, where the mixture, which is this rock, we're interpreting this rock as being a product of magma mixing. So every rock that's listed here is a product of mixing, is going to be mixing between some mafic end member with a certain concentration of silicon and magnesium and a felsic end member that has some different concentration of silicon and magnesium. And my end members are over here in terms of silicon and magnesium, and I've also added K2O and P2O5. The mixing model is down here. So we've done these calculations earlier. If I take these data and plot them, so I'll copy these and enter them into this chart. The end members that are shown up here are plotted in the orange symbols, and we'll do edit, paste special, a new series, categories, X values in first column to show the line. The line looks not too bad. It seems to go through the middle of the data. But what I want to show here is another way to look at how good the model is. How well is it explaining the mixing of these samples? So the first thing we need to look at is when we calculate the silica content and we look at the amount of mafic material, XM, notice that we're taking this value here, and when we calculate MgO, we take that very same value. So in our model, the XM, the amount of mafic material in any particular mixture, does not change, and it should not. So what we can do is rearrange this equation, take this equation, rearrange it. Well, first we rearrange it here, recognizing that there's only two components. So that means the felsic material is equal to 1 minus the mafic. If we take mafic and felsic and add them up, it should be the whole thing, 100%. So we first make this substitution, and then we rearrange to solve for the mafic component. So the mafic component, the amount of mafic material in any mixture, is this difference, this ratio of the difference between the mixture and the felsic and the mafic and the felsic. So let's just dive in and do the calculations. So from the silica content, the amount of mafic material in any mixture, and again, each rock represents a mixture, will be this numerator, mixture minus felsic. What's the mixture? The rock itself, the observed silica is the mixture, minus the amount of SiO2 in the felsic end member. And so that's this guy here. And I'm going to put a 3 in front of that row so I can fill down and not change the felsic end member reference cell. And then in the denominator, I just want the difference between the mafic and the felsic end members. And so I'll take that difference and again put a $sign in front of the 3. I'll hit return. And so what this calculation says is that based on the silica content here, that observed silica content, this rock is 42% mafic end member, and the rest, about 60%, a little bit less, 58% would be felsic. I can do a fill down to do this for all of the samples, and you can see how the amount of mafic material varies for each sample. So each sample is a mixture, but each mixture has a different amount of mafic material. This guy here with higher silica contents in row 7 requires less mafic material than something with lower silica contents, like this guy up here. But here's the trick. I've calculated it from the silica content. I should get the exact same numbers if I do the calculation for magnesium. So that's what we'll do here. For magnesium, we'll take, for the numerator, mixture minus felsic. So the mixture is this guy observed minus the felsic end member, that one there, divided by mafic minus felsic. And again, we want to lock in the referenced cells for our model end members, and we'll fill down. Notice that we don't get the same value. if the silica content says this sample LT96-3H from Dome A is 42% mafic material, but the MgO says it's only almost 30%. Over here, the model works a little bit better. This one says 44, this one says 47. So for some, we get pretty close agreement. For some, the agreement is not very good. So what we could do is check all of the samples that we have to see how good our model is as a whole. And so we'll take the difference between what we get from the silica and the MgO contents. So these two are different by 13%, or 0.13 is a fraction. A little trick in statistics is we like to deal with positive numbers. And so we can make these positive by taking the square. We could also take the absolute value. But when you deal with statistics, you'll hear a lot about the sum of squares. So this will be the squared difference. And we'll calculate that for each sample. And then we could take the sum of the squares. We'll just add up all of those squared differences. And the better the model, the lower the sum of the squares. And so if we wanted to, we could play with the mafic and felsic end members here and see how it changes that number. So for example, if we have 1.1% MgO in our felsic component, maybe 1.05 would be a little bit better. Let's see if it changes 1.132 and causes it to be lower. Oh, it does. We get a slightly lower value. So we improved our model by shifting the composition of our felsic end member a little bit. We could play with all four of these numbers to try to get this number to be as low as possible, or in other words, for these two values to be as in close agreement as possible. They'll never be in perfect agreement. Ideally, in a perfect model, this would be 0, and because these would all be identical, but nature doesn't work that way, and our models don't work that way. There's a certain amount of sloppiness, which means that magma mixing probably doesn't explain everything. There might be other things going on that explain maybe some fractional crystallization that explains some of these variations. So it's mostly magma mixing, but maybe not entirely magma mixing. So we can play games with that. If you really think this line is due to magma mixing, this linear trend, there's another trick we could do. We can go to chart design and we can add a trend line and put in a linear trend. And that trend line is there. We'll see if we can click on it. Yes, we can. We'll display the equation and the r squared. And we'll zoom in here. This is the equation. The y in this case is MgO, and the x value is SiO2. So it's telling us that MgO is equal to this quantity 0.9197 multiplied by silica plus a constant 15.091. What we really care about is the r squared. The r squared, when we multiply it by 100, is the percent variation explained by that line. So if magma mixing is the cause of this linear trend, then magma mixing is explaining about 86% of the variation. But that means that there's another about 15% or 14% of the variation that is this spread here that's not being explained by that linear trend, that might be due to something else, which could be an error in our analyses. There's a certain amount of error when we analyze these rocks, although there's probably not that much error to explain all that. It could be the way we collected our samples, or it could be that magma mixing is not the only process going on and there's other stuff going on. Anyway, in a mixing model, in theory, these estimates of the mafic component should match for every single oxide. We should be able to do K2O versus P2O5, which I've done over here. And we could set up another mixing model. And you could try the same trick calculating that amount of mafic material based on K2O and P2O5. And you'll find out if you do that, you'll get a very different answer. In part, that's probably because these oxides are in very low abundances and they can be pushed around. Potassium is mobile through through fluids migrating. It's fluid mobile, so that could affect the results. Anyway, that's the basic test. We'll end here and maybe do another video on linear regression, other ways to test the quality of your magma mixing models.